sorry, if I just remind you where we are in our lesson, this is the first topic of P1, which is quadratics, and we are learning all about everything about quadratics. We first looked at what a quadratic expression or a quadratic polynomial means, or simply we can refer to it as a quadratic. It's something in the form ax squared plus bx plus c, where a, b, c are numbers, but a cannot be 0. So it's an expression with the highest power of x is 2. You need the x squared term for it to be a quadratic. And we just began to see that any quadratic can be written in 3 different forms called standard form, factorized form, and complete square form. Usually quadratics are written in standard form. That's the usual way of writing. That's the way they are. That's called standard form. And many quadratics can be factorized. Sometimes you can't factorize. So there are quadratics that cannot be factorized, so cannot be written in factorized form. But complete square form is something that all quadratics can be turned into. So this is what we learned. We learned how to factorize a quadratic and how to turn a standard form quadratic into a complete square form. And I was just beginning to discuss what are their usages? Why do we even write the same thing in different forms? Why do we need that? Because we have nothing better to do? No, people have come up with these different forms because they have different advantages and benefits of their own. Okay, so last week, I left you with a question. I wanted you to think about, I was kind of trying to lead you to something. I don't know whether you thought about this. I don't know whether you even remember what I'm talking about. I asked you, if I give you a certain quadratic in standard form and ask you, now you know that since you have x in your quadratic, you have an unknown letter. That unknown letter can be any number, right? Like if I give you, if I say x squared minus 3x plus 4, this is a random one, I don't know, right? And you know that if you plug in different values for x, the value of this whole expression would take different values. So, you know, you can make a table x, and if I call this whole thing, if I call it like y, if I call it y, you will see that when x is 0, this has some value. When x is 1, it has some value. When x is 2, it has some value. When this is 2.3, it has some value. When it is minus 1, I mean, there are so many values you can put for x, and you can think of different values that the whole expression gets. My question was, is there a largest value that this expression can be, or a smallest value that this expression can be? And if so, for what x value does that happen? When I put what x value into this, do I get the smallest possible value for y? Or when I put what x value into this expression, do I get the largest value for the whole expression? Are you able to immediately say that by looking at this expression? That was my question. Did anyone think along that question? I don't know whether you are dropping messages. Okay, no. So it looks like, okay, so keep thinking about it at the back of your mind. The answer will come in today's lesson, okay? Right, so let's go back to the note. And we are going to start, so this is what we did last, right? I hope you all have this. This is how to, changing a quadratic into standard form. So the forms discussion is over. Your next topic, if I take you back to the very beginning of the summary of the topics, so we discussed quadratic polynomials and expressions. The second topic in line here is equations, but this time with you, I'm going to do a small experiment. And I'm going to change the order of the topics a little bit. I think the different order would benefit more. I just want to see whether that will have a different effect, okay? I'm going to talk about functions first before talking about equations. Now, even in your book, equations comes first. That's the usual sequence. But I have a feeling that if we talk about functions first, that would make better sense when we go to equations. Okay, so I'm actually changing the two topics here. The second topic we are going to discuss, that we are going to start today, is quadratic function. So this is a place where you see a quadratic, where in quadratic functions, you know what functions are. You're familiar. You have a certain familiarity with functions to some extent. You haven't learned in detail, but when I say function, you know, you have some sense of what I'm talking about. So we are going to be looking at what quadratic functions are. So put your next topic to parallel to, so your 1.1 was like this: quadratic polynomials or quadratic expressions or simply quadratics. Your second topic that we are starting today, 1.2, is quadratic functions. Okay, so let me go to that. So on a, maybe on a new page, or if you like, you can just start wherever you are. The quadratic function, or you can say quadratic functions. Okay, shall I make it quadratic functions? I think that makes, because we want to start with quadratic with the Q. The quadratic functions. Let me make it quadratic functions. Okay. So just write the topic. Let me go to the board before you see. Now I have a little thing happening today. If you drop me a message, it doesn't pop up on my screen unless I go and check whether I have received any messages in the chat. So I might not immediately see if you tell me something. So that's a big bad thing. Okay, so I will time to time go and check the chat box. I'm sorry about that. I don't know why that is happening. And also I don't see the thumbnail on my screen. It's gone on my screen. Right. So quadratic.
Excuse me, miss?
Yes.
Yes, I don't know why in my screens
there is a black box.
Yes, miss.
See, yeah. So that happens. Okay. Please move. You know, even yesterday this happened. This happens sometimes. I don't know why that is. Whenever so I will tell you why you see that black box. If I am opening the chat box, where the chat box is, you see a black box on your screen. If I take my taskbar at the bottom of the screen, if I take now you will be seeing a long rectangle at the bottom of the screen. That's my taskbar. Like now it's gone. So if I take something up on the screen, you see it as a black box. I'm sorry about it. So I will try my best not to pull up other windows on my screen, because if I do, you are going to see it as a black box. So actually what that would mean for today's lesson is that you have to talk to me if you have to say something, because if you drop something in the chat box, I would have to open it, and then you will be seeing black boxes. Okay, I hope everyone has their microphones working, and please, for today, this happens sometimes. I don't know what the reason is. It's something to do with Zoom. So please, just whenever you want to say something, please just speak and say it. Okay, right. So quadratic functions. Now let us think about what a function is. We have, if you can remember the topics in P1, we have a separate topic, a chapter called functions. And we are yet to go to that chapter, but we are talking about quadratic functions here. That sounds like, are we learning something? We are learning something about functions. We haven't even learned what a function is. You might think like that, but you have some idea of what a function is, and that little amount that you know is enough to learn about quadratic functions. Okay, but later down the line in P1, you will be properly learning about what a function is and everything about functions. But for now, can you tell me, from your knowledge that you have so far, what do you think is a function, and what kind of functions have you learned so far and familiar with? Can someone tell me? Give me an example for a function that you know. You might not be able to say what a function is inwards, but you might know examples for functions. What are some of the functions you know?
F brackets x equal 3x plus 5.
Wait. Can you say that again? Is that Afra? Now I don't see also who's talking, right? Is that Afra?
Yes, Miss Afra.
Yes, Afra. Can you say that again?
F bracket x.
What bracket X? X.
F.
X.
F.
F. Oh, F bracket X. You said, oops. You're saying F bracket X, close bracket?
Yes.
Okay.
Equal 3x plus 5.
Right. Very nice. This is a function. This is a function. Now, I want everybody to pay very close attention. Okay. How you read this is f of x. How do you read this? F of x. Let me write it. F of x. That's how you read that notation. It's the notation for a function. Instead of f of x, you can put y there. You can say y is equal to 3x plus 5. Okay? There are a number of different notations. These are just notations. In math, we come across so many notations. It's like the language of math. Why do we have notations in math? Because we like to write long things short in math, right? And these notations are very useful. With the f of x notation, I can easily say, if I say f of 2, you know what that means. That means put 2 in place of x. Now, if this is my function, or what Afra gave me, it is a function, good Afra. If I ask you, what is f of 2? What I'm asking is, what do I get when I put 2 for x? So that is 3 times 2 plus 5. Right now, you're familiar with these things. So that is 6 plus 5. So f of 2 is 11. That means when x is 2, f of 2 is 11. Or when x is 2, y is 11. Okay? So a function for now you can think of as a relationship between x and y. Right? Or even better, remember I told you when you have, even better if you think like now, if you look at this expression, the expression Afra had in the function she gave me, 3x plus 5. In a function, what we do is you think of different values that this whole expression can take for different x's. When you put different values for x, what are the different answers you would get for? So you label the whole thing as f of x or, oops, f of x or y. So this can be f of x or y. F of x means the value of the whole expression. Okay. So when you write an expression by labeling it as f of x or by labeling it as y, right? That is called a function. For now, that's not the proper definition of a function, but for now you can think of it like that. Okay. Now, so when you write it like that, f of x equals 3x plus 5 or y is equal to 3x plus 5, it's the same thing. You are kind of representing this whole table. Think of an infinitely long table with all the different values x can take and all the different corresponding values y will take. So when you, that's what is represented by this. Versus when you just have 3x plus 5, the expression. The expression is just the expression. When you say y is equal to 3x plus 5, you are thinking of all possible x values along with all possible y values, right? You're thinking of all these pairs of, like, if I may use the word coordinates. So you know that a function can be represented in a graph. You can plot all these points and check out what the shape of the graph of this function is. So what you're familiar with so far are what are called, the example Afra gave me is an example for such a function. These are, what function are these called? Does anyone know? Now this 3x plus 5, y equals 3x plus 5 is an example for a what function? What's the term? What's the word? Does anyone know? They are called linear functions. Have you not heard of that term before? Linear functions?
Yeah.
Maybe, yeah, okay, right? These are called, the example you gave me, 3x plus 5, y equals 3x plus 5 is a linear function because the expression in your function is a linear expression as opposed to a quadratic expression. What do you mean by linear? A linear expression is an algebraic expression with the highest power of x, 1, right? And it's called linear because when you graph it, you get a line. So it's a linear function. It's easy to remember the word. Okay. So like this is the mx plus c form of a straight line graph. So if you have mx plus c form in a function expression, that's a linear function. Okay. So you are familiar with linear functions. If I just quickly say that again, a linear function is when you have f of x is equal to what the expression you have here is a linear expression. Oops. Now that happens because I'm sweating on my palms and fingers. When your expression there is a linear expression. Linear means the highest power of x in your expression is just 1. So you will have an x term and maybe a number term, okay, like the one Afra gave me. So when this is a linear expression, we say this is a linear function. And always a linear function, when you draw its graph, it's a line like that, or no, like it's a line. So you talk about the gradient of that line, intercept of that line, and all that. Right. So then now you can imagine what a quadratic function is. A quadratic function is when you have f of x equals, your expression is a quadratic expression in that function. So something in the form ax squared plus bx plus c. So this, when this is a quadratic, f of x is equal to a quadratic, then it's a quadratic function, right? Simple as that. And you can think of then, if I think of all the values, if I take different values for x and write what the f of x is, and if I plot all these points, what kind of a shape would I get? You can talk about this function and its graph and its properties and things like that, okay? So that's what we're going to do. So let's go and first copy the first part of the note. If you have any questions, you have to stop me and ask, please.
Excuse me, Miss.
Yes.
What if the highest power of x was 3 or 4?
Very good question. So now you see, now this question came out because of you already saw a pattern. So if the highest power is 1, we call it a, sorry, let me go back to this screen. If the highest power is 1, it's called linear. If the highest power is 2, that's a quadratic function then. What if I have a power 3? Yes, you can go on like that. Power 4, power 5, highest power 3, highest power 4, highest power. So all these expressions have names, and you will be learning about all this in P3. Now the question you asked is actually from the content in P3. So I'm very happy that you thought about this question came to your mind. So let me spend 1 minute, because this is very this is a good trend. Okay, I want everyone to be excited about this. So if an expression in the form ax plus b is linear, an expression in the form ax squared plus bx plus c is a quadratic, highest power 2. An expression in the form ax cubed plus bx squared plus cx plus, I'm going to be needing more letters, you see that, plus d is called a, does anyone know the name? This is linear, this is quadratic. Does anyone know the name for this polynomial? It's a
Cubic.
Cubic, very good. It's a cubic polynomial. Then you can have power 4, ax to, oh, wow. Ax to the power of 4 plus bx cubed plus cx squared. I hope you can see the pattern. Cx squared, that's a square, plus dx, that's a d, plus e, that's a power, has power 4 polynomial. It's called a quartic polynomial, and so on. These are what are called polynomials, and these are polynomials of different, we say, degrees. Okay, this is degree 1, degree 2, degree 3, degree 4. So in this topic of quadratics, we are only learning about these polynomials and places where they appear. Okay, so quadratic functions, quadratic equations, quadratic this, quadratic inequalities, quadratic that, all places where quadratics appear. So if when you have a good understanding of a quadratic, you can deal with it when it appears in certain other areas. So you will be learning about cubic ones, quartic ones in general. When you know the general pattern, you can predict, then if it is 6, this is what it is going to be like. You know, you will get the whole sense of the whole family of these different polynomials. Okay, that was a very good question. Oh, I'm sorry, somebody has dropped a message. Senitu, now I know that you will be all seeing a big black box in the middle. Let me move it to the side. This for a cubic equation, can't we factorize out an x and solve the quadratic equation if there are only 3 terms in the, yes, of course, Senitu, that is exactly right. If you only have 3 terms, only up to this in a cubic equation. Now he's talking about the equation. Equation means if you have this is equal to 0, this is equal to 0, this expression equal to 0. If you have, it's a linear equation, quadratic equation, cubic. This is, see how you can generalize this to all possible things. Okay. So linear expression. Notice the word I'm using. Just if you think of what I have written here, these are expressions: linear expression, quadratic expression, cubic expression or polynomial. Okay, quartic polynomial. If I form an equation by saying this is equal to 0, this is equal to 0, this is equal to 0, if I form an equation, now I have a linear equation, a quadratic equation, cubic equation, quartic equation, and so on. Or if I say f of x is equal to ax plus b, f of x equals ax squared plus bx plus c, f of x equals ax cubed plus bx squared, and all that. Those are linear function, quadratic function, cubic function, quartic function, and so on, right? So Senethu's question is, he's asking, if in a cubic equation, if you only have the x terms, if b is 0, so this is 0, there's nothing here, and equals to x, yes, you can factor an x out, and then you will be left with a quadratic. You can factorize the quadratic, and you can solve it to find all the 3 solutions of the cubic. That's the other thing. A linear equation has 1 solution, a quadratic equation has 2 solutions, a cubic has 3 solutions. The equation I'm talking about, equation, okay? So don't mix these up. You have to know very clearly what the expression is, what the equation is, what the function is, what each of these mean, and what they represent, okay? Think about this and try to digest it and try to, what happens is when you work with this a lot and when you contemplate these ideas a lot, they become part of you. They become very natural to you. So that's the kind of, what do you call that? It has a nice name. I forgot the name. That's the kind of, not skill, but let's say a skill for now. That's the kind of skill I want you to have. Right, shall we write this first introduction sentence? A quadratic function is a function in the form f of x is equal to, you have a quadratic, ax squared plus bx plus c. So you know that here a, b, c can be any numbers with the condition a cannot be 0. If a is 0, it's not a quadratic, right? You know this already. So write this down. Okay, when you are done, you have to tell me as much as possible. Try to talk without dropping messages, because I will try. Okay, I hope everyone is done then. Actually, I am going to give you a 1 minute or 2 minute break to drink some water. Now, you all must be drinking water throughout. No, I can't see you. This actually is something that we have to do. I was not doing this before. We have to take a tiny break like every 45 minutes, because in this online mode, especially compared to the physical mode, the attention span usually is 45 minutes. You get a little tired after 45 minutes trying to, you know, absorb everything that is said. So take a little small break, maybe 1 minute or 2 minutes. I will also I'm just seeing that my water is over. I will quickly get some water and zip some water and come back. Just 2 minutes. Okay, take a 2 minutes break. I hope you all took your little break. Like stand up from your seat if you've been sitting throughout, especially because I know that like if you have been having classes throughout from morning, I hate to do this to you. So that's, I will make sure that I give you little breaks like that. 1 minute is, 2 minutes is enough for you to like stand up and, you know, stretch, maybe walk around and come back, so that you have that monotonous form is gone. Okay. Hope everyone is back, right? Okay. So, and you all have copied this now. Now, we are going to look at how the graph of this function looks like, okay? And before that, I will quickly say this too. Now, just like with linear functions, with a quadratic function, now just think about this, okay? Think about how the expression, just having the expression is different from having the function. Expression is only this part, only this part. This is the expression. Oops, wait, I'm trying to, that part, this is the quadratic expression. With that, we have formed a function now. We are calling it f of x is equal to this expression. When you do that, you are showing a relationship between x and f of x. So you are thinking of the relationship between different values you can put for x and different values that this whole expression can take. When x is this, the expression value is this. When x is that, the expression value is this, and so on. So this kind of covers all those different values of x's and the value of the expression. Okay, so you can talk about what is f of 1, what is f of 3, what is f of -5. So you just simply plug in that value for x and think about the value of the whole expression. That is called the value of the function, right? Now, when you think of the graph of this function, what we are thinking is, if I plot taking this x and y, f of x can be called y, taking these different x's and corresponding y values, and if I think of them as pairs of coordinates and plot them on a grid, xy grid, and connect these dots, what kind of a shape do I get? So if you again go back to your linear functions knowledge, when you have a linear function in the form y is equal to ax plus b, and you draw a little table and find some points for different points of x, the different values of y, and plot them, you get a straight line. Similarly, if you do the same thing for this quadratic function now, what kind of a shape do you think you will get? Does anyone know?
A U shape.
A
U shape.
A U shape. Okay, you're very close. Okay, it looks a bit like a U shape. This shape is called a parabola. Okay, it is not a U. The arms of that opens up, keeps opening up, and gets wider and wider and wider as you go up. A U, on the other hand, is like its arms becomes vertical finally, right? And they go parallel like that. So this shape is called a parabola. Okay, so the graph of any quadratic function, just like the graph of any linear, 3x plus 5 minus 2x plus 9, I mean any linear, ax plus b, whatever a, whatever b you put, it's always a straight line, right? Just like that, for all the quadratic expressions you've seen so far, if you think of the corresponding function and plot it and draw the graph, it's going to have a parabolic shape. It's called a parabola. Okay, so I have drawn here the graph of the most basic quadratic you can think of, which is f of x equals just x squared. Okay, so I want you to quickly sketch this and write this. The graph of any quadratic function takes a curvy shape called a parabola. Make sure that you sketch it properly. Actually plot a few points. I have shown here the values for -2, -1. Just look at these values. When you square, do you see that all the even when you put negative x's, your y value becomes a positive? So it goes like that. So this is what is called a parabola. I have shown in green dots where these points are, and make sure you get the shape right. It's not like a U, it opens up. The more you draw it, the wider it gets. So
Excuse me, Miss?
Yes?
Miss, is this a quadratic function because it doesn't have a plus b in it?
Oh. Now that question is, can you think about that question again? Let me go to the board. A quadratic function is, okay, who's saying something? Senitu has asked, Miss, can we tell a quadratic function is another form of a quadratic equation? No, it's not. The quadratic equation is something else. Quadratic function is something else. Let me get to it in a little bit. Let me address, I think it was Afra. Afra, you asked what? You were not sure whether that was a quadratic because it didn't have the. Now this is what I had, no? Now remember in this, even, okay, that's a C, sorry, my C, okay, that's my C. Here, B and C can be any number. B can be 0, C can be 0. Okay, remember, isn't this a quadratic expression, x squared? Isn't x squared a quadratic expression?
Yeah.
It is. So why is this not a quadratic function?
So Miss, it's fine that b and c are 0?
Of course, that's exactly what we mean when we say A, B, C can be any real number. Isn't 0 a real number?
Yes.
Yes, so B and C can be zeros. So in your quadratic, you might only have, wait, I will take you back to the note a little bit. I think it looks like you have forgotten something. This is what this we discussed on the first day when we started quadratics. Let me go back up, all the way back up. Here we said, where A, B, and C are any real numbers with the condition A is not 0, because if A is 0, you will not have your squared term. Okay, and we said a quadratic has at most 3 terms. At least x squared term. Okay, it's the x squared term that makes a quadratic. And look at these examples here I gave you for quadratics. I gave you all different kinds of examples just to emphasize the fact that you can not have the x term. You might not have the number term. Look at the 5th example here, 5x squared. It is still a quadratic. It doesn't have the x term. It doesn't have the number term. Look at the 3rd example, x squared plus 2. Where's the x term? No x term, because b is 0. Right? So don't always think you have to have all the 3 terms. Who said that? Nobody said that. At most, you will have all 3 terms. But both the 2nd and 3rd, the x and the number terms can be 0 if b and c are zeros, isn't it?
Yes, miss. Thank you.
Hey, you're welcome. I hope now that that kind of are others clear with that? Do you have a doubt that f of x equals x squared? Is that a quadratic? Because it doesn't have the x term. It doesn't need to have the x term. For an expression to be a quadratic, it only needs to have the x squared term. If you have the x squared term, it's a quadratic. The highest power of x is 2. Other terms might be or might not be there. Okay? And Senithu's question was, I'm sorry, you will be seeing black boxes when I open this. So let me read Senithu's question. While you are copying this, just listen. So originally he asked, Miss, can we tell a quadratic function is another form of a quadratic equation? No, that is not correct. A quadratic equation is not another form of the quadratic equation. A quadratic equation is one thing. A quadratic function is a completely different thing. They are 2 different things. Okay. Then he goes on to say, Miss, in physics we learned that, for example, throwing a stone off a cliff maybe, the stone follows a parabolic path. That's correct. So can we assume that there can be a quadratic function for the path of the stone? That is exactly correct. That is correct. The path of anything that you project, the word is project. Projecting, now this is with physics, by the way. For anyone who's not doing physics, I'm sorry, but this is good stuff to know. Whenever you project something, means now I can project something vertically upwards, right vertically, so that it follows a vertical path. I'm not talking about that. I'm talking about anything projected at an angle. Okay, maybe like this, like when you throw a ball, a net ball, when you shoot with a basketball or a net ball, when you throw a stone like that, you know, at an angle, they all follow the path that they follow is a parabola. Senithu is very correct. And it can be modeled, that path can be modeled by a quadratic function. That is exactly what a parabola is. Okay, so after this class, you go and throw something in the air at an angle and see how it's going. That's what a parabola is. That's very correct. Okay, so so that path can be represented with a quadratic function, because each point on that path gives you a pair of x and y coordinates that follow a relationship between x and y in a quadratic function. Okay, now this here I have drawn the simplest quadratic function. I have made it as simple as possible. You can't make it any more simple. This is the simplest quadratic function. F of x equals x squared. Not even like 2x squared, 5x squared, just x squared. Okay, but for whatever quadratic function that you now think of a more complicated expression like minus 3x squared plus 5x plus 100, still it will be a parabola. So the only thing, like the curvature, how much it opens up might be different, it might appear in a different place in the grid, but the shape is this shape, okay? Or it can come upside down. We will discuss about that. It won't tilt. It's symmetric. Okay, now we'll discuss about the features of this graph in a moment after you have finished copying this. Are you done copying this?
Yes, miss.
Okay, I hope everyone is done. When now I will move on when one person responds saying you are done copying. Okay. Okay, here are some words or terms that you have to be familiar with. So the first term is parabola. It's the name of the shape. Now, this means any parabola has a turning point. Okay, comes like that, turns and goes back up. Or if you have you can have the parabola the other way around, like upside down. Then it comes up. It has again, it turns and goes back. So it has a turning point. This bottom point is called the turning point. And if we give a special name to it, it's called the vertex of the parabola. Okay. And the points, if your parabola happens to cut the x-axis, now you can see that if this parabola appears like a little above the x-axis, it won't be cutting the x-axis. And this particular parabola we have sketched is cutting the x-axis, or rather touching the x-axis at 0 on the x-axis, 0, 0, origin. Okay, you can have a parabola crossing the x-axis at 2 places. If I move it like little down, it will be cutting the x-axis at 2 places. So if your parabola is crossing the x-axis or touching it, these points are called the roots of the function. So this particular function has one root, that is 0. That's the point on the x-axis where the parabola crosses it or touches it. Okay, and then any parabola, any quadratic function has a line of symmetry. This is a symmetric shape. Remember, it won't come tilted. It's like that with a line of symmetry going through the vertex. Okay, so all parabolic graphs, all quadratic functions have a line of symmetry. So can you copy that 2, 3 sentences? So these are the features of this graph. And please do keep those questions, keep them coming. I like when you ask questions, and that's how you should learn. That's how learning should happen, you know. Just think of every, just let anything come to your mind related to this lesson that we are doing, and just ask me any question that you want. So I'm glad Senithu brought up this. They are called projectiles. The path of something that is projected at an angle, they follow a parabola. And let me know when you are done, please.
Excuse me, miss.
Yes.
Miss, there are green dots on the graph, right? Do
Yes.
those indicate something?
So they are I have in a table, I have found some coordinates here. I have plotted them. Those are the points. -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4 I have shown.
Okay, thank you, miss.
And you connect them to get the shape, right? So I have just plotted only a couple of points. 1, 2, 3, 4, 5, just to show you how the shape comes. And then with the arrows, I'm indicating that this continues up.
Done, miss.
Done. Okay, I hope everyone is done. Let us continue. Now, let's learn some features, okay? Some features of the, now if I give you a quadratic function, now remember we learned that a quadratic can be written in 3 forms. So if I give you a quadratic function, in my function expression, I can be giving you the quadratic in standard form, I can give you in factorized form, I can give you in complete square form. Or if I give you a function, you can turn the function into a different form, because a quadratic can be written in 3 different forms. So that's an interesting thing. Let me go to the board a little bit. What I'm saying is,
excuse me, miss.
yes.
Please, can you show the slide a little bit? I couldn't copy some parts because of the black boxes which appear.
Yeah, sure. This part?
Yes, miss.
Okay. Let me know when you're done.
Done, miss.
Okay. So let me go back to the board. Say I give you a quadratic function. So let me just say f of x equals, I'm going to take, if you have your homework, I'm going to use the quadratic that we had in the first, the 25 expressions I gave you. I'm going to use the first expression I have there. So I'm forming a function using that quadratic. So my function f of x is equal to x squared plus 6x plus 8. Okay. Now, I have given you a quadratic function. And the quadratic in that function, this is the quadratic, is written in standard form, right? Since you all have the same expression already written in factorized form and complete square form, let me just, for the fun of it, write it that way too. So same function I can write, if I wanted to, in this way. I'm just copying from, okay? Just check your books. This is the first question you had in the homework. The expression you had, the first expression you had in the homework. So that is, it's still the same function. Is this a different function? No, same function, right? I just written the quadratic in a different form now. These are what a form means. Same thing in a different form. Now, this word form, I want you to understand properly, okay? It doesn't mean it's a different thing. It's the same thing. But it's the same thing in a different form. Let me think of it. I think I told you like a different analogy. I actually used to show, let me see, I might have it in my phone. I used to show earlier to students, it's like, if you know Lady Gaga, she has a, do you all know Lady Gaga?
Yes, miss.
Yes, right? Let me show you Lady Gaga in different forms. It's the same person. She could look so different. Here's Lady Gaga. I don't know. Let me see if I can, like, I don't know whether you see this. This is Lady Gaga. Are you seeing her?
Yes, miss.
Right, okay. This is the same person in a different form. Okay, funny. Same person in yet another form. Okay, so my point is, the forms means it's just a different outfit, kind of, you know, same person, same thing. So that's the meaning of a form. Form doesn't mean it's different. So this word is very important. We will be coming across this word a lot. Okay, and also we know the same expression can be written in complete square form. You have done it. So let me write my function. I'm writing my function f of x with the quadratic in it in complete square form. X plus 3 squared minus 1. Okay, let me erase this word form here. Okay, and remember I told you that each of these, being able to write a quadratic in different forms, And each of these forms have their own benefits. Here's one place where each form comes in handy and helps us tremendously to visualize the graph. Now we know that this, if I graph this, it's going to be a parabola. But on the grid, now let me draw I'm going to graph this function. Okay, so here, oops, that's not the way it should come. It should come this way, and then this way. So these are my XY axes. I know now this is going to be a parabola. Now it can come, I don't know where it will be placed on the grid. Now y equals x squared was a perfect one, right in the middle, crossing through the origin, very symmetric, it's right in the middle and all that. But this one, x squared plus 6x plus 8, where would that be? And would it cut the x-axis at maybe 2 places? Would it be upside down? Like, these information you need to be able to sketch it. You can't be drawing up a table and finding x points and finding y points like the usual method of plotting a graph. You can't be going into all that hassle. But this helps us to sketch this graph. Let me show you. Now, in the standard form, the first form, this one, in this form, it gives me a very important feature of the graph. In standard form, it tells me where the parabola cuts the y-axis, the y-intercept. Just like in a linear function, here is the y-intercept. And that makes sense. What do you mean by y-intercept? Where the graph cuts the y-axis. And when a graph cuts the y-axis, what can you say about the x-coordinate? X-coordinate is 0. Put x0 here. What do you get for f of 0? You get 8. Okay, so the standard form, when you have the quadratic written in standard form in your function, a piece of information that you can immediately extract about the graph is the y-intercept of the parabola. This parabola has to cross the y-axis at 8. Is that clear to everyone? I need a simple one response from one person, yes or no. Is that clear to everyone?
Yes, miss.
Okay, good, right? Now let me mark 8 on the somewhere. So let this be 8. I know that this parabola has to go through 8. Now one more thing, I said your parabola can come this way or this way. That is determined by the sign of the x squared term. The sign of the x squared term. If the x squared term is positive, positive means smiling. It's a upright parabola, smiling one. If the x squared term is negative, it's a sad parabola. That's how you can remember it if you want. Okay. So just by checking the sign of the x squared term, now are you able to check the sign of the x squared term in the factorized form? In this form, can you check it by looking at it? Yes, you can. Like if you think of multiplying x times x, that's going to give you a positive x squared. In the complete square form, when you square that, x square is going to be positive. In all three forms, that can be easily identified whether the x square term is going to be positive or negative. Okay. So since the x square term is positive here, positive x square term, I know that this parabola has to be a smiling one. And it has to cut through 8. Now, I don't know whether it's going to go. Let me draw two options. It can be going like that, or it might be going like that. You know, so we don't know for sure which one it is. But these two pieces of information we already have from the standard form. Let's go to the factorized form. Here's how it is very useful. Factorized form immediately tells you where your graph cuts the x-axis. Let me put label the axis here, x and y. Because when your graph cuts the x-axis, y-coordinate is how much? At a point when you're on the x-axis, what's the value of y? Now this is your graph knowledge. 0, right? When y is 0, that you're on the x-axis then. So You just have to think this expression f of x, I need to be 0 if I'm thinking of where it's cutting the x-axis. And we know that this becomes 0 when x equals -4 and when x equals -2. Is that right? Let me write it here. When x, because if this x is -4, that whole thing would be 0 and this will be 0. So my y or f of x is 0. So that's one point where my parabola has to cut the x-axis to be on the x-axis. And also if that x is -2, it will be cutting the x-axis. It will be on the x-axis. The y value will be 0. So I know that when x is -4 and -2, my parabola has to cross the x-axis. That information I can never get from standard form. You look at the standard form, does it tell me that? But the factorized form readily tell you that. So this is one benefit of having written the quadratic in your function in factorized form. The two factors tell you the roots of the function. Now I can sketch the graph. Here I go. Now I know it has to go through, so it has to be like coming like that, cutting like that, cutting through this, and going like that through 8. Going like that. Right? What about this form? Doesn't that tell me, give me any information about my function or the graph? It does. Here's what the complete square form tells me. It tells me the coordinates of the vertex. It exactly tells me where the vertex is, where the turning point is. How is that? How is that? I will let you think about it. So this parabola goes like this. It has I can call it a minimum point. The value of my expression has a minimum. It can't be anywhere. It can't go below than that. When you keep plugging in different x values, at this x value, whatever the x value here, that's where the value of my quadratic takes the smallest value. Before, for x values before that, my value of the expression is higher than that. After that value of x, my value of my expression is higher than that. At this particular x, I have the minimum possible value for my y. Look at the complete square form.
-3, -1.
-3, -1. When x is, this expression could be minimized. What the minimum you would get for that expression if this part is 0, isn't it? Because it's a square, it will always be a positive number. So you have to think of when would it be 0? It would be 0 when x is -3. Then you will get the minimum value for your, so this is -3. And then when that is -3, your value of f of x is just that number, -1. So the complete square form has this piece of information embedded in it. It's this number, the negative of this number, and this number itself are the coordinates of the vertex. -3, -1 are the coordinates of the vertex, and that information is embedded in the complete square form. And in the factorized form, the roots are embedded in it. In the standard form, the Y-intercept is embedded in it. Like these different informations appear in each of these different forms. Okay, so this is why it is useful to know how to express the same quadratic in different forms. You can extract different information when it comes to talking about the quadratic function and its graph. Okay, is that clear to everyone what we discussed so far?
Excuse me, miss.
Yes.
To find the x coordinate of the vertex, you can also add the two x solutions and divide it by 2 since it's symmetrical about the vertex point.
That's very correct. Wow, I'm so happy that you figured that out. Did anyone think of that? Now this is a symmetric shape. If you think,
Miss, that's how I gave you the answer.
is it? Wow, wonderful. Now, when you know the two roots, they are equidistant from that point where you get your minimum or the maximum. Say if it was a graph like that, still this point is would lie right in the middle of those two roots, right? So you can simply add them and divide by 2 to get that midpoint. That's another way of figuring out the x coordinate of the vertex. Wonderful. Oh, wow. Very nice. Okay. So see, when you're really in this, you can see so many things and understand so many things. That's wonderful. Okay. Any more discoveries or questions or anything like that before we start copying the note for this? Okay, looks like no. And before you start copying the note, I will quickly show you just to convince you that any quadratic that you will give me, oh, there are so many messages. I'm sorry. I'm so sorry. Because as I told you, I don't see when you message me until okay, let me go up. Senitu. Then how can the curve cut the y-axis if the two x coordinates are, okay, you got it. -1 is, you have given me, okay. Oh, the graph of the graph y coordinate. Yeah, nice, nice. Okay, then you got it too. Right, let me take you to, first I have to open this, give me a moment. Okay, it's okay. I'm going to take you to a different screen now, just to convince you that any quadratic that you can think of always gives a parabola. This is a graphing tool. It's called Desmus. I think I don't know whether I have mentioned this to you. I will be using this a lot to show you graphs of different functions. Tell me a function. I'm going to show you. We will just, when I give the function here, it will graph it for me. So let's check out different graphs. Can someone throw a graph at me? A quadratic function. A quadratic function. F of x equals, throw me one. Let's see whether it's a parabola.
X squared plus 7x minus 9.
X squared plus 7x plus 9? Plus 9. There you go. There's Afras, I think. Afras parabola. Another person. Give me a quadratic. And put any A, B, C. Maybe B and no B, C. Quick. Another one. Somebody. Are you okay? You're dropping messages. No? Senator, we do sometimes when the graph goes flat at the minimum value. What do you mean graph goes flat at the minimum value? At the minimum value, only for that point it's flat. It doesn't stay flat. It doesn't stay flat. You don't get, your parabola doesn't go like it comes down and it comes to a minimum, it stays in the minimum for a while. Like it doesn't stay flat. Okay, momentarily it's flat. Only at that point it's flat and it goes back. So you're saying sometimes when the graph goes flat, it doesn't go flat. It becomes flat for only in that point. At the minimum value, what do we do if it expand over weight? So that doesn't happen. So that is your question. It doesn't happen. The minimum happens only at one point, momentarily. Just like, yeah, very good. So if you think of the projectile, it reaches that height. Does it stay at that height and then fall back? No. It reaches a height and comes back. It happens in 1 second and in one moment. Okay? It's just one point. That point is just one point. It doesn't stay flat. Good, Senitu. Can someone give me another quadratic? Make different signs, different numbers. Go wild with this. Just let's check out how these parabolas differ from each other. Quick. We have to write the note also. Someone, if you're not giving, let me try. Let me try with minus 2x squared minus 3x plus 12. It's a huge one. I need to read. To be able to see it, I need to zoom this like that. Okay, you see it now? So it's a sad parabola, but it's still a parabola. It has a maximum. Okay. Let me draw something just with an x squared term. 5x.
It's half x squared
half x squared. There's my 5x squared. Here's half x squared. Half x squared. Now notice certain things. Because of the half, your parabola is a little fatter. Let us put an even smaller number there. 1/10. 1/10 x squared. That's very fat. You see? So you can explore, you know, how these numbers, the different effects that these numbers that you can play around with have on the shape of the graph. They are all parabolas, but different curvatures, fat, thin. Did someone have a question for me? I thought I heard something.
Excuse me, miss.
Yes?
Can you draw a graph for a quadratic equation where the x solutions are not real?
Yes, let me draw one for you. Let me try. Okay, so I have to get, so now, yeah, there's something to notice here. For all the graphs that I have sketched here, they all somehow either cross the x-axis or at least touch the x-axis. Okay, let me remove all this. It looks a mess. Let me remove all of them first. Let me show you a quadratic. I have to like make a, did you get, okay, let me just quickly make one. So for that, that's my pen, it doesn't write. I can just randomly try. Okay, let's say 2x plus 13, something like that. You see that? This parabola is hovering above the x-axis. It doesn't cut through the x-axis. Okay, or let me, if I reduce this a little bit too. So.
Mister, how about an equation where the x coefficient is not 1 and also the equation doesn't have a x solution?
I didn't understand. So can you give an, what do you mean by that? It doesn't have a coefficient.
The coefficient is not 1.
Not 1. Okay, like say 2x squared, and it doesn't cut down. So you mean like this? So I can put a 2 here. See, the bigger the number I put here, the thinner the quadratic gets, the parabola gets. The coefficient of the x squared term is what determines how fat the parabola is. So if you want a thin parabola, make sure the x squared term, the coefficient of the x squared term is huge like that. Or if you want a fat parabola, make sure you have a very something close to 0, like 0.1. See how fat it got, and the whole, you know, the placement got changed too. Let me make it 0.01. Oops, sorry, 0.1. It's so flat that it has gone out of my screen. Not flat, I mean, so yeah, so fat. Huge parabola. Okay, so my point is this: however much you play with these numbers in your quadratic, ax squared plus bx plus c. Okay, this is the function. Let me first what, otherwise this will come. This is your y equals. This is a function, y equals. Okay, so you have x, y, different points on this curve. Whatever quadratic you have, they all have a parabolic shape. That doesn't change. It's just that where it is, how fat it is it upside down, is it upright, all that are determined by these numbers that you put, A, B, C. But they are all parabolas. This is what I wanted to show. Okay, so good. We had a really good discussion. Let's write everything now. We have to write the notes now. So I am giving you in point form each of these different features that we can extract, or information that we can extract from, by looking at the expression in the quadratic function and how the different forms tell you different information. Okay, so you start with a sentence saying some features of the graph that can be expressed from the quadratic expression are, and a colon, and I'm giving you in point form. So the first point is this, and then you have to do the small, oops, wait. Okay, so the first point is Just the sign of x squared term in the quadratic in your function can tell you the orientation of the parabola, whether it's a smiling one or whether it's a sad one. Quickly copy this. So I have just taken an example. For simplicity, I've taken x squared function, okay? But for any function, this is true. The sign of the x squared term tells you whether you have an upright parabola or an invert or upside down parabola. I can actually add the word, if that helps you. I call this happy parabola. And this is sad. That's easy to remember. Happy face and sad face. Let me know when you're done copying. Oh, there is a message. I'm sorry. Let me check this message. Senitu is asking, Miss, if somehow, I'm sorry if you're seeing a black box now. Miss, if somehow a biggest number existed, there, there is no biggest number, Senitu. So if somehow, so he's saying, hypothetically, if that existed, will the graphs go vertical if that number was used for coefficient of x squared? Hypothetically, yes. But it doesn't happen because there is no biggest number. So that's a good thought to entertain. Okay, yeah, it would be so thin. Okay, send it. When you are done copying, let me know. These are just sketches. Okay, these are just sketches to show that this and this. So don't spend a lot of time, copying the graphs. Just sketch it to show the shape, the smiling and sad parabolas.
Done, Miss.
Done. Okay, I will assume that everyone is done when one person responds. If you need more time, let me know. Second point.
Miss, I need more time. There's a black box hovering.
Oh, sorry. Okay, yeah. Let me know when you're done. Just sketch this. You don't even have to show the scale on the axis. Okay, this is just to show the shape. Are you done? See, I'm also using these words minimum and maximum. When you have a happy parabola, your function reaches a minimum point. Your function has a minimum value. When it is this, your function has a maximum value. You can't get a higher value than that with this expression, whatever x you put. Okay, so just make a note of that. Okay, here's the second point. The y-intercept can be easily read when the quadratic is in standard form. So I've given an example. Again, when you sketch, just draw a sketch. You just need to show that it is cutting through 3. The y-intercept is 3. That's all you need to show. Done.
Done, miss.
Okay, hope everyone is done. Here's the third point. The roots of the function can be easily read when the quadratic is in factorized form in your function, right? And I've given an example.
Miss, can you scroll up? I didn't copy the graph.
Okay. Now, so while you're writing, let me just tell you something.
Done, Miss.
Okay. Oh, there is a message. Miss, can we tell that when the gradient of the parabola is 0, that point is the minimum or the maximum value according to the graph? Yes, Senitu. Yes, that is very right. Did everyone hear that? It's only at that point, the turning point, the vertex, that is the only place where the gradient of the parabola is 0. Very good. Yeah, this is actually your questions, your comments have a relation to the topic differentiation that will come later. I was going to say, I keep hearing, and through voices and through messages, I keep hearing only the same set of, that was Lishan all the time messaging, isn't it? Lishan, na? Senitu. Senitu is someone who responds a lot. Lishan also responds. Afra, Aisha, Tenumi Umasha has responded to the Akitmi. Not everyone. I would like everyone to talk here. Okay, we have to have a discussion. It's a discussion. We are all exploring this. So, just for the others who have not talked at all, I'm just reminding you. Please, try to say something. If maybe you have questions. Now make sure, oops, sorry. Make sure that you understand. Do you all understand how do we know that the roots are 3 and minus 2 from the two factors? Do you realize that? When the graph cuts the x-axis, y coordinate, y has to be 0. F of x has to be 0. F of x or the y will be 0 if one of these two factors is 0. That would happen when either x is 3. This is the same argument you use when you solve equations, quadratic equations. So this is not a new idea. Let me know when you are done copying.
Done, miss.
Okay. Last point.
Teacher,
Yes?
Can you keep the graph?
Yes. Yes. So just sketch it. In that sketch, I want you to show the cutting points of the parabola with the x-axis, where it cuts the x-axis at -2 and 3. And also notice other things. I mean, you can see that it's a smiling parabola because if you remove these brackets, your x squared is positive. And in your head, you can also figure out the constant term, -3 times 2, -6. So the y-intercept of this is -6. I have not shown it, but all that also you can see. But we are focusing on the feature, it's just the roots.
Done, miss.
Okay? Last point. The coordinates of the vertex can be easily read when the quadratic is in complete square form. Now, while you copy this, let me say, remember last time, I think it was either Afra or Aisha, you were asking whether when you write in complete square form, whether you can put that, if you get a number in front, whether you can put it back in the bracket. This is why it is not a good idea to do it. You have to keep it out so that you can readily see the coordinate. If it's x -3, then +3 is the x coordinate where the vertex happens. If you bring the 2 in, it will ruin that information. So in your sketch, you can with dotted lines show the coordinates like 3, 2. That's with dotted lines, which show it. Let me know when you are done. And one more thing, let me know when you're done. I want to go back to a previous note.
Done, yes.
Done. In this, which point? In this first point, can you, in your sketch, please mark put an arrow to this point right here. I hope you can see where my pointer is, right here. And label it as your minimum. And in this sketch, label that vertex point as your maximum place in your sketch. Just label when you have a minimum, that point is the minimum. When you have that point is the maximum. Just mark the point, which is the vertex. The vertex can be called as, in this case, minimum, in that case, maximum. Because there you have here you have the minimum value for the function. Here you have the maximum value for the function. Okay. Right. I'm going back down. Then I am going to give you a small exercise to practice sketching the graph of a quadratic function when I give you
Can
the
you show the next point, Jayakody?
next at this point, this one,
This one.
yeah. Okay, done. Let me see whether I can. Are you all done?
Yes, miss.
Yes. Okay. So let's quickly do. You might not be able to, but let's see the time. We have 10 minutes. Okay. A small exercise to quickly do. Write exercise after this. Write exercise and write this question. I will read. Oh, there are messages. I'm sorry. Let me read them. From Senithu again. Miss, is this the same graph with the same function we discussed in the previous example? Miss, can we tell that if a graph is a minimum, it doesn't have a maximum and vice versa? Can we tell that if a graph is a minimum, it doesn't, I mean, if it has a minimum, it doesn't have a maximum. Of course, it's because it's a parabola. It has only one turning point. It's not going to go like that and again, that doesn't happen. If you have a minimum, that's all you have. If you have a maximum, that's all you have for a quadratic function. And yes, you can say whether it's a max or a min just by checking the sign of the x squared term. Okay? And I think each of these examples are different. I've not taken the same function. These are all different functions in each bullet point that I've taken. Right, so your exercise is, write the question, sketch the following quadratic function, sketch the graphs of the following quadratic functions. Sketch the graphs of the following quadratic functions. Okay? Sketch the graphs of the following quadratic functions. And I am going to give you some from the homework that you've done. Let's see, okay. I will write in the board. Number 1. Sorry about this black box. Number 1, I will write here. Number 1. Oops. F of x equals x squared minus 6x plus 8. So I have given you the function, quadratic function, with the quadratic in it, written in standard form. So not a lot of information can be extracted with this. You can see whether it is smiling or sad, and you can see where it is cutting the y-axis. Roots, you can't see where the roots are. You can't see the coordinates of the vertex. If you need those, you have to change the form. But this is the second example in your homework. So you already have turned this into factorized and complete square form. So you can use those information. Number 2. So I'm going to give you a few from what you have in your f of x equals x squared minus 10x. Again, this is one quadratic in your homework. Number 3, f of x equals x squared plus 3x plus 9. Number 4, y equals, I'm giving in a different notation, y equals x plus 1 squared. Different form, not the standard form, different form. Number 5, y is equal to x plus 4 squared minus 2, again a different form. 6, y equals minus, open bracket, x minus 2 squared plus 1. Number 7, y is equal to x plus 1 times another form, x plus 3. You can always like turn back and forth between your forms if you need different information. Last one, number 8, y is equal to 2 minus x, x plus 1. Okay. Can you start sketching this? Or we can leave this for homework. What do you want to do? Let's see. Anyway, we don't have time to start the new topic. Let's just check the first one. Can all of you do the first one? Sketch the first one and we'll leave the rest for homework. Okay. And if someone can, you can switch on your video and show me your graph, your sketch. That would be lovely. And for your information, you have this expression in your homework. Or if you can't show me your graph, let me know when you're done. I will show it on the screen. So when you are asked to sketch the graph of a function, sketch means it's not an accurate graph. It's just a sketch means, you know, it's an approximate rough graph. But you have to show the key features, key points in your graph. For example, the y-intercept, the x-intercepts. The x-intercepts are the roots in this case. And here, for a parabolic graph, you have to show the coordinates of the vertex. So y-intercept, the two roots, if they have roots, you might not have roots, okay? And the coordinates of the vertex. These are the things you have to show in your sketch. So while you are slowly doing it, let me also go to a new page and start sketching the first function. If I write the function first, I have given it like, I have given the expression in the function in standard form, x squared.
Miss, is this correct?
Are you showing me? Oh, the thing is, wait, then I have to go to the, wait. I have to stop share. Can you lift? I can't see the full, I can't see your, can everyone see? I hope everyone can see this. So it's a smiling parabola. This is Afra's solution. Thank you, Afra, for sharing this. So it's an upright parabola, that's correct. And the where is the y-intercept of this? You have to show the y-intercept, where the parabola is cutting the y-axis. So I think if you extend it, it looks like it's going towards the right direction, but you have to show it. It's cutting the y-axis at what point? At 8. Can you keep it back? Okay, it's okay. At 8. And I think your roots were right. Can you show it back? from the factorized form, you know that the roots of this function are -4. Oh, your roots, your roots are 4 and 2. So that is correct, Afra. The 2 points where your parabola is cutting the x-axis, that information is correct. So that's right. And the coordinates of the vertex are 3, -1. That is correct too. So that is all correct. You just have to show where it's cutting the y-axis. It has to go up and cut through the y-axis at 8. So yours is almost correct. Okay. I hope everyone else got that. So let me quickly go to the, thank you, Afra, for showing that. I was just going to do it here. Oops, sorry. 6 - 6x plus 8. This was what I had given you. But the same expression can be written as you have already written it. X minus 4, x minus 2. And also you can write it as x minus 3 squared minus 1. So from that x and y, it has to cut at 8. It has to cut the x-axis at 2 and 4. And then it'll be like that. That's very ugly. But this point would be 3, -1. So this would be -1 and that would be 3. Okay. So my sketch is very, very ugly. But that's because I'm writing, I'm writing on a touch screen. So that is not very, it doesn't turn out very nice all the time. So I hope you all got that. Did you all get that? So you have to show all the features. You have to show the 8, you have to show the 2, you have to show the 4 and the vertex point.